Okay, so I just want to look at one last thing that can happen here with that type of substitution, where you might think that you have to use partial fractions, but you actually don't. So I have the integral of 2 over 3 plus the square root of x dx. This is the problem where the substitution is really obvious. I'm going to let u equal to the square root of x. Letting it be x, not helpful. Letting it be the square root of x gives us a really easy way to proceed. So u is equal to the square root of x, which means u squared is equal to x. Anytime we let u be a radical, we immediately square both sides, and then I get 2u du is equal to dx. So I'm going to replace that dx right there with 2u du. So then when I rewrite this integral, I have a 4u up top, and then a 3 plus u down on the bottom. Now that 4 is a constant, so I'm going to bring it to the outside of the integral. So this is 4u over u plus 3 du. Now, this is a rational function. U plus 3 is a linear factor that occurs one time. What that means is that partial fractions isn't going to be helpful because I only have one denominator. The derivative of u plus 3 is 1, but I have that extra u on top. So that substitution to turn this into a simple ln is not going to work. But what I see here is that the degree of the numerator is equal to 1, and the degree of the denominator is also equal to 1. So we could do a typical long division, and I'm going to do that off on the side here. Typical long division, where I say let the bottom, u plus 3, goes into u. U divided by u is 1, so that's u plus 3. That I'm subtracting, and I get a negative 3. So that this would give me 1 minus 3 over u plus 3 du. And that's really straightforward, and it is a totally valid way to approach the problem. But when the degree of the numerator and the denominator are both 1, we actually have a really simple type of division that we can do. We can do this long division in just like a super fast way that doesn't involve us going and writing it down like this. So, or what I can do is multiply by 1 and add 0 to make the numerator look like the denominator. So what I mean by that is up here, I don't really have anything to multiply by because I already moved the 4 to the outside. Those u's are the same. I want the numerator to look like the denominator, so I'm going to add 3. And now I have u plus 3 on top and bottom. But I can't just add 3 to a numerator. That's changing the value. So I must also subtract 3. So what I have here is u plus 3 minus 3 over u plus 3 du. And now I'm going to take this denominator and distribute it to 2 parts of the numerator. So this gives me u plus 3 over u plus 3 minus 3 over u plus 3 du, which results in the same thing I had over there, 1 minus 3 over u plus 3 du. And now both of those resulted in the same thing. Both terms in this integral are really straightforward. This is equal to u minus 3 natural log of u plus 3 plus c, and u was the square root of x. I'm forgetting to bring my 4 with me, so let me write that 4 back down. Equals 4, 4, we want to multiply by 4. So this is equal to 4, the square root of x, minus 12 natural log of the square root of x plus 3 plus c. So either one of these division methods is totally valid. This one really only works in the case where the degree of the numerator is equal to the denominator. Okay, so that's my final answer here, and I'm just going to do one more problem really quickly that doesn't start with a substitution, but that shows us again how this method of division that I just did works. I also want to point out before I do that though, I also could have done another substitution with this problem where I let w equal to u plus 3, and that would also work. I'm not going to do it. I'm just going to write down that it's possible here. So, or we have this third method, let w equal to u plus 3, dw equals to du, and u is equal to w minus 3. This substitution, the second substitution, will also work. Okay, so here we started with a substitution and it turned into a division where we didn't actually need to do partial fractions because that division turned it immediately into a known form. We could have used a substitution in the same way. Let's just do this one other example so I can show you what I mean again by this method. Make sure that you're following. So let's say that I have 2x over 3x plus 5 dx. Well, the first thing that I notice here is that the degree of the numerator and the denominator are both 1. I have a 3x on the bottom, but a 2x on top. So I'm going to start by bringing the 2 to the outside. So I'll have x over 3x plus 5. Now, I want to have 3x plus 5. So I'm going to multiply by 3 and divide by 3. In the same way that I do when I'm doing a substitution, I'm multiply and divide by the same number because then I'm multiplying by 1. But then I also want that 5. So I'm going to add it, but then I have to subtract it so that I've just added 0. So then what I get here is 2/3 the integral of 1 minus 5 over 3x plus 5 dx. Now I'm going to do the preliminary step in green here just to show what happened. This is 2/3. I distributed that 3x plus 5, first to the 3x plus 5, then to the 5. And in this way, I did my long division without actually having to go through the process of doing long division. Really fast, easy to follow. I turned this into 2 simple known forms. So this is 2/3. The antiderivative of 1 is x. This is a known form. I have to divide by 3 because the derivative of 3x plus 5 is 3. This is our known form, ln of ax plus b, 1 over ax plus b. So it's minus 5/3 natural log of 3x plus 5 plus c. I'm just going to simplify this 2/3 x minus 10/9 that natural log. Just to remind you of the known form that we are using, k over ax plus b dx is k over a natural log of ax plus b plus c. So that's what we were using in this problem. Now, to be noted, could you do regular division? Absolutely. Could you also do a substitution with this problem where you let u equal to 3x plus 5? Yes, you can. That will also work. So there are oftentimes multiple ways to approach a problem. All right, that's all, guys. Bye.